Does an object have to be hot to have heat? A physicist would say no. Ice cubes and even liquid nitrogen can contain heat. Heat is the measure of thermal energy being transferred from one object to another. It's designated with the variable Q. Because Q is a measure of energy, we use energy units for this value. The most common energy units used are calories and joules. If heat is the transfer of thermal energy, what is thermal energy? Thermal energy is the kinetic energy of atoms or molecules that make up a substance. These atoms and molecules move around by rotating, vibrating, and in the case of liquids and gases, even translating. The energy of motion, in general, is kinetic energy. When tiny particles, atoms, and molecules perform this kinetic energy or motion, we call it thermal energy. The word thermal energy probably sounds a lot like the word thermometer to you. If so, good. The temperature of a substance, as measured by a thermometer, is actually the average thermal energy of the atoms or molecules in a substance. This is why the Kelvin temperature scale is so useful. At 0 Kelvin, there is no kinetic energy and no motion of the atoms in a substance. On the Kelvin temperature scale, as the temperature goes up from 0, the motion increases and thermal energy increases. Temperatures can be easily converted from Celsius to Kelvin using this relationship. Tk equals T degrees centigrade plus 273.15. As the temperature rises, the thermal energy of a substance increases. The opposite is also true. As the temperature decreases, the thermal energy of a substance decreases. The heat transferred, Q, can be calculated as Q equals mc sub P delta T. In this equation, C sub P is the specific heat capacity of a substance, m is the mass, and delta T is the change in temperature. Always calculate the change in temperature by subtracting the initial temperature from the final temperature, T sub F minus T sub I. If the heat is transferred into the substance, the thermal energy of the substance will go up, so Q will be positive. If the heat is transferred out of the system, the thermal energy of the substance will go down, and Q will be negative. The specific heat capacity is a constant that specifies how much energy must be put into 1 gram of a substance to raise its temperature 1 degree Celsius. This can also be thought of as raising it 1 degree Kelvin, because the size of a degree in both of these scales is equivalent. This constant can be measured or found in reference books for each phase of each substance. It's good to note that different phases of the same substance have different heat capacities. For example, the specific heat capacity of ice differs from the specific heat capacity of liquid water. This table shows the specific heat capacities for some common substances. Note that when using specific heat capacities in calculations, the substance must remain in the same phase. Phase transitions do cause heat to be transferred, but are calculated in a different manner. Let's look at some examples. Example 1. A 5.0 gram gold ring is lying in the sun. The ring absorbs 20 joules of thermal energy. Assuming that the ring starts at a temperature of 30 degrees Celsius, what will the final temperature of the ring be after absorbing this energy? First, insert all the known values into the equation. Since the specific heat capacity is in units of joules per kilogram per degree Celsius, we'll also need to convert our mass of 5.0 grams to kilograms as well. The specific heat capacity of gold is listed in the table. 20 joules of heat equal 5 grams times 1 kilogram per 1,000 grams times the specific heat of gold, 129 joules per kilogram degrees Celsius times the change in temperature, T final minus 30 degrees Celsius. Then, solve for the final temperature. 31 degrees Celsius equals T final minus 30 degrees Celsius. T final equals 31 degrees Celsius plus 30 degrees Celsius. T final equals 61 degrees Celsius. Example 2. 1 gram of an unknown substance loses 11.2 joules of thermal energy when cooled from 90 degrees Celsius to 65 degrees Celsius. What's the specific heat capacity of the unknown substance? First, we'll algebraically isolate C, the specific heat of the unknown quantity. We'll plug in our known values, remembering to convert our mass of 1 gram to kilograms. The specific heat of our unknown substance is equal to 449 joules per kilogram degrees Celsius. Based on the table, we now know that the substance must be iron. Let's review. Heat, or Q, is a measure of thermal energy being transferred to and from a substance. The most common energy units used are calories and joules. Thermal energy is the kinetic motion of the atoms or molecules in a substance. The temperature of a substance is the average thermal energy. On the Kelvin temperature scale, 0 Kelvin is the point at which all motion stops, and a substance has no heat and no thermal energy. Specific heat capacity is a constant that specifies how much energy must be put into 1 gram of a substance to raise its temperature 1 degree Celsius. Heat can be calculated for one phase of a substance that's changing temperature by using this equation. Q equals mc sub p delta T,